to Tania Morimoto, Thesis Defense. I'm Allison Nakamura, her proud PhD advisor. I just want to give a little intro before she gets started with her talk. It's been a joy having Tania in my research lab. One of the things that you probably won't hear about today, because it's not part of her thesis that she work in our lab, is build some of the first Haptics, these educational haptic devices. And Tania is a student who is crazy enough to help me host an online, massively online open course involving haptics. And that was the first research that she was really deeply involved in the lab, and then it expanded into very different areas, as you'll see later. Now, usually in these intros, I like to roast my students a little bit. Tania's pretty hard to roast, actually. I mean, I could fault her for liking her kawaii Japanese things, or for running too much, but I can't really fault her. And in fact, one of the things I did want to say is that sometimes people joke that Tania and I have a lot in common. You know, we're both half Japanese. My kids will go to the high school that she went to, and there's a lot of commonalities there. But actually, it's really not about me. It's really that I want my daughter to be just like her. So in addition to being adventurous and trying new foods like durian and winning this paper award, it's probably the thing that I would most like my daughter to be like is as fast as a runner. So this is my daughter Nora, and Tania's run a couple of races with Nora and encouraged her to her personal record in the 5K. But of course, Tania has made many other friends on campus. Of course, she's an integral part of our research lab and a good friend and support and collaborator to many people in our group. And then also, of course, to her friends and family. This is a picture of Tania and Sean. Tania is one of the few people who didn't go skiing during one of our lab retreats, but instead went out in the cold to run. Good shot here. And then also I want to acknowledge Grant, Tania's fiance, and also all of Tania's family for joining us today, family and friends. So thank you for joining us. And Tania is now going to present her PhD research. And I'll let you swap it. I don't know how. There's two more chairs up here if anybody wants them.
Three, actually.
Well, thank you for the introduction, Allison. And thank you everyone for coming today. Today I'll be talking about my PhD work on patient-specific design of concentric tube robots. So I want to start by talking a little bit about robotic surgery and how this compares to traditional surgical methods. As you can see on the picture from the left here, traditional open surgery involves making a large incision in order to open up the entire abdomen of the patient. And this is necessary for the surgeon to be able to get his or her hands completely inside the patient's body, for them to be able to see everything that's going on. And this results, as you can imagine, in large scars and long recovery times. Laparoscopic surgery involves making small incisions or ports inside the patient's body, through which the surgeon can then insert various tools. And while this is much less invasive, it can often lead to more non-intuitive movement of the tool since you're operating through a remote center of motion. And robotic surgery also has the potential benefit of being less invasive and the additional added benefit of having more dexterity inside the patient's body. So there's a number of existing robotic systems, a few examples of which are shown here. And these are all built in order to operate and perform a number of different procedures. And so they're built to have a varying number of degrees of freedom. And there's also a large number of different ways that you can actually control these robots, although the main one is teleoperation. So I have a video here of the Da Vinci surgical system. And I'm sorry, if you're squeamish, don't worry, this is not real. It's foam and rubber and stuff. And what I want to show from this video is that in teleoperation, you have the surgeon working at a master console. And as the surgeon moves his or her hands, the patient side robot, shown on the top, follows the same movement. And so this can add increased dexterity as well as control during these robotic surgeries. So there's a number of potential advantages of these robot-assisted minimally invasive surgical systems, mainly due to the fact that we have now these small ports or holes inside the patient's body rather than these large incisions. So these can lead to a number of improvements for the patient, including reduced pain and scarring, as well as a faster recovery time and fewer number of complications. And these improvements are hard to come by simple manual tools, but by adding the robot into the loop, we can add additional enhancements for the surgeon as well, which can then lead to these improvements for the patient. And some examples of enhancements for the surgeon include increased dexterity, vision, as well as control. So despite these large number of potential benefits of robotic systems, there still remain a number of open challenges. And so these systems are built in order to accommodate a wide range of different patients, as well as a large number of different procedures. And because of this, these systems are built to be highly general, sort of like a template system. And this works really well for the general population, but it tends to marginalize certain specialized patient groups, such as pediatric patients, as well as obese patients. And so what my PhD work is focused on is this idea of, can we actually personalize these template systems in order to create smaller, more specialized robots that are customized for a particular patient as well as a particular procedure. And so the reason that these robots don't necessarily work as well for these patient groups is they have their anatomy is slightly different, and because of this, these template systems may not prove as effective. And so in order to have this idea of patient-specific design, we need to develop a new workflow. So what we have here is the following. So starting with preoperative images, such as CT scans, is what we use, but you can imagine using ultrasound images, MRI images, etc. We can then build up a 3D model of that particular patient's anatomy. And we can use that model to actually design a set of personalized surgical tools for that particular patient. We can then fabricate these personalized tools and then use them in an actual procedure. So this slide really shows the bulk of my PhD work. But before I sort of dive into each of these steps, I want to take a quick step back and go through a little bit of background information. So first, I want to talk about a little bit of technical background and what are the actual surgical tools that we're going to be talking about. And then second, the clinical background and motivation for this work. Okay, so starting with the technical background, the particular robots that we're interested in using are part of this larger class of robots called continuum robots. You can see here they're these highly flexible robots, and they can be thought of as having an infinite number of joints with links of 0 length, so that they essentially have infinite number of degrees of freedom. And these can transverse in confined environments really well, and can also conform to highly curved shapes. Often these are inspired from biology, including trunks, snakes, and tentacles. And an additional benefit is they are often pretty easy to miniaturize due to their inherent structural compliance. Now, in particular, we have been focused on using concentric tube robots, which are part of this larger class of continuum robots. So shown here are examples of what concentric tube robots are, and they consist of this series of hollow, pre-curved tubes that nest one inside the next. So it's a little hard to tell from the video, but if you look at the picture down here, you can see there's 3 tubes actually nested inside of each other. And these all have a different pre-curvature to begin with. So as you insert and rotate each of these tubes with respect to one another, you get this bending in free space that you can see in the video here. And this comes from the fact that each of these tubes has its own pre-curvature, and as the curvatures overlap, you end up with some equilibrium curvature in between that of the original tubes. And so researchers have been looking at using these types of robots for procedures, such as endonasal procedures and cardiac procedures, but we've been particularly interested in using them for urologic procedures in pediatric patients, which I'll explain next. In addition, researchers have used these, have developed various control models and kinematic models for these, but there's still a lot of open questions about the design as well as the fabrication of these robots. And one more reason that we're interested in using them is that concentric tube robots lend themselves really well to this idea of patient-specific design. And that's because all of the parameters, including the lengths, the curvatures, the sizes, can all be adjusted based on the particular patient. So to ground our work in a specific clinical application, we've been working with a pediatric urologist who came to us with this problem where in pediatric patients, there's certain sites within the kidney that can be really difficult to reach using traditional methods. So as you can see here, usually they might use a straight needle in order to access some disease sites such as the kidney stone. And while this works really well in adult patients, pediatric patients have a much more compact body, and so everything is much closer together, and you risk puncturing something else along the way, in this case the pleural cavity or the lung. And although some clinicians try to take alternative paths, such as one shown here below this last rib, that also has downsides in terms of adding increased forces against the patient's body. So what we've been interested in is how can we develop a way to enable safe access to these hard-to-reach sites within the kidney via some type of curved or nonlinear path. And what we've been interested in accessing are both kidney stones as well as renal tumors. So a little bit about those. Kidney stones affect about 2 to 3% of pediatric patients each year. And the standard surgical treatment is called percutaneous nephrolymphotomy, which involves this straight needle approach that I was. No, I think I just have a new clip up. So they use this traditional straight needle approach. But again, this is not great for pediatric patients. In addition, we're interested in accessing renal tumors, which account for about 7% of all childhood cancers. And in this case, the main surgical method for removal is relatively invasive. They actually remove all or part of the kidney. And it wasn't until recently that researchers have been looking at percutaneous access, so through the skin here, and they would actually percutaneously access the kidney and then stick an ablation probe through the access sheath in order to basically heat and get rid of that damaged tissue. And so what we've been interested in for both these kidney stones as well as renal tumors is how can we enable the surgeon to have a safe access path to this disease site, and then once they've gotten there, they can stick the appropriate tool, such as an ablation probe, through the concentric tube robot in order to get rid of this diseased tissue. So now that we have a little bit of background, I want to go over a quick outline of the rest of my talk today. I'm going to start by talking about the design of these robots. So how do we actually design a set of patient-specific concentric tubes? Next, I will talk about the fabrication of these personalized robots. Third, I will talk about how do we actually control these in some type of surgical procedure. And then finally, I will show a demonstration of this entire patient-specific design process. So starting with the design. When we think about designing these concentric tube robots, there's a large range of different parameters that we can actually control for. So that we have the outer diameters, the inner diameters, the length of the straight section of the tube, the length of the curved section, as well as the curvature itself. And then we also have to actually select how many of these tubes are we going to use. And for any given configuration of these concentric tube robots, what is the relative insertion distance between the tubes as well as the relative rotation? And so you can imagine this design space can get relatively large. And so many groups have used various optimization algorithms in order to design these tubes for a various task or optimize depending on the workspace. But what we've been interested in is, can we actually leverage the expertise of the surgeon to help us in this design process? So the idea behind this is that the surgeon is the expert in both these procedures as well as the patient's anatomy. So is there a way that we can add the surgeon into this design loop to actually help us design these patient-specific tools? So what we've developed here is what we call this surgeon design interface. And the surgeon's actually immersed in this virtual reality environment wearing the Oculus Rift head-mounted display and can actually help us design these set of tools. So the way our interface works is we start with these CT scans, and we can segment each of the organs in the area of interest, so CT scan by CT scan, until we can actually build up a reconstructed 3D model of each of the organs in the area of interest. And we can combine those into one entire patient-specific model, which we can then import into this virtual reality type environment that we've developed. And the surgeon can view this patient anatomy then through the Oculus Rift headset. And he uses this Phantom Omni haptic device as both an input device into our system as well as to receive some haptic feedback during the design process. And the last component of our system are these foot pedals, which are the foot pedals that they use for the Da Vinci surgical system. And the idea behind using this is we have various modes of our interface. And in order for the surgeon to be able to switch between them without looking at anything, since he's wearing this head-mounted display, surgeons are pretty used to these foot pedals, and so they can use these instead. So before the surgeon can actually start designing, there's a few parameters that he needs to select based on the patient size as well as the tool size that's going to be passed through these particular set of tubes. And then the remainder of the parameters can all be adjusted while using the design interface itself. So we have 4 modes in the interface. The first is this initialization mode, so the surgeon can actually create the initial set of concentric tubes. Second is design mode, where the surgeon can adjust each of these different tube parameters. And then we have a camera mode, where the surgeon can view things from different angles. And then finally, playback or simulation mode, where the surgeon can view what it looks like if you're actually deploying this robot through the patient's body. So I'm going to play a few videos now so you can get a better sense of what the interface looks like. But just a few things about the videos is the first thing is that for each of these, I'll be showing a 3-tube concentric tube robot, where each of these colors represents a different tube. And the blue tube is the outermost tube, so the largest, and the orange is the innermost tube. And then one other thing about the videos is that for all of them, I've displayed the robot away from the patient anatomy just to make it easier to view what's going on. But when the surgeon's actually using it, he has the robot close up inside the anatomy. So to start, this is what it looks like when someone's actually interacting with the interface. And they start by placing what we call these via points. So these are points through which they would ideally want the concentric tube robot to pass through. And after they place these, we can compute a set of tube parameters that would give us a configuration of the robot that can pass through those points. And then once they have the initial design, they can actually move the concentric tube robot through space and reorient it with respect to the anatomy. So the way that we actually initialize this design is by taking those via points that they've placed and fitting a spline through the points. And we do this by fitting circles to each of the segments using 2 points and a tangent vector. And then we can back calculate from there the tube parameters. Once we have the tube parameters, we can compute the forward kinematics, which then gives us the configuration of the robot, shown here in green. And then we need to find how we can actually align it back with the initial via points that they placed. And then we can actually show them the configuration shown here. And so that's how they see their initial design. So I want to show an example of sort of some of the interactions that the surgeon has with the interface in order to change some of the parameters. So here's an example of how they can change the length of any of the individual tubes. So they start by, there's these white tabs that I have located at the center of each of the tubes of the robot. And they can grab one using the Phantom Omni and one of the buttons. They can use the cursor, grab the tube, the white tab, and actually drag the cursor along the length of the tube. And it changes, the cursor changes color to match what tube they're changing. And when they release that button, we can then compute the forward kinematics given the new tube parameters and show them what the configuration would actually look like. And similarly, they can do this for the curvature as well, where they can grab the white tab and this time sort of stretch or compress what that curvature would look like. And we can again compute the kinematics and show them what it would be like. So here's a video of both of these actually happening. And something that you can't see is that we're actually rendering a simple spring force as they're changing the length. So as they're pulling the cursor further away from that equilibrium point where they initially started, they feel a force kind of pulling them back, which gives them a little bit more of a reference to how much they're changing some of these parameters. And again, here's just an example of them changing the curvature, sort of stretching it out, and then recomputing what it would look like and showing them the actual configuration with the changed parameters. The next one I want to talk about is this camera mode. So they use those foot pedals to change into the next mode. And then this giant sphere appears around the anatomy, and it's rendered with a surface stiffness so they can actually feel when they run into it. They can grab it and drag it around to any orientation they want, or they can use these sort of presets with the buttons in order to view everything from a different angle. And then they can also use the foot pedals to zoom in and zoom out in order to get a better view of during this design process. And then the last mode is this simulation mode. And in this, what we want to do is show them what it would actually look like if they were deploying the concentric tube robot. And again, this is pulled out from the patient anatomy just to make it easier to see. And what we show here is there's many different possible deployment sequences. So basically sequences of insertions and rotations. But here we show what's as close as possible to what we call follow the leader deployment, where the backbone most closely follows the tip as possible. And they can pause it and restart it and watch the process. So we wanted to do a short demonstration to show our pediatric urologist actually using our interface. So we had him design a set of tubes to reach a kidney stone in a pediatric patient. And we let him sort of play around with the interface and the different modes for a while. And once he was familiar with it, he spent about 6 minutes designing the first set of tubes. And the second time, it took him around 3 minutes. And so we think this shows the potential for this type of interface and that it can be rather intuitive and quick to learn. And we think that it shows that there's this potential to actually use the expertise of the surgeon and have them help us in this design process. Okay, so now that we have this digital model and design of these tubes, I'm going to talk a little bit about how we actually fabricate them. So concentric tube robots are typically made with nitinol, which is a super elastic shape memory alloy. And in order to actually create these shapes, people basically make a jig that's in the right curvature, and they bend the nitinol into that shape and heat it up to the desired temperature in order to get the desired shape. And this works really well, but there's a few challenges in terms of maintaining that super elasticity of the material once it's cooled back down. And also, when you pull it out of the jig and it relaxes, sometimes you end up with a slightly different curvature than the one you designed for. So other researchers, and as well as us, we were interested in how can we actually look into and come up with other methods and materials for making these robots. So what we proposed is to use 3D printing to make these robots. And we believe that this works really well with the idea of patient-specific design, because 3D printing makes it really easy once you have the 3D model to then make the physical 3D model of it. And so while 3D printing may seem a little bit strange in the context of the medical field, there's actually a large number of existing examples in the medical field already. So 3D Systems, for example, has actually made this, what they call exosuit. And so they did a 3D scan of the entire patient's body, and they 3D printed a fully customized and functional, exoskeleton for this particular patient. There's also a company called Haptics, which scans patients' arms and then actually prints very durable and much more comfortable casts for each particular patient that they see. Researchers have also been using them in order to print models in order to study anatomical nuances of particular patients. And so they can use this to actually plan a procedure based on that particular patient's anatomy. And researchers have also used it for simulation. So they've actually printed the particular patient's anatomy, allowed the surgeon to actually practice stitching and cutting in order to understand that patient's anatomy better. So when we first started looking into materials, we decided that it was important to also understand some of the design requirements and constraints for selecting particular material for this process. So this chart just shows some of the constraints put on by the patient size and the tool size, and how we can actually start designing these robots. So first, the size of the patient is going to determine what the maximum size of this outer diameter, the largest outer diameter, can be. And then the smallest inner diameter of the innermost tube is going to be dependent on what the tool size is that you actually have to pass through this concentric tube robot. And then the remaining diameters can all be determined based on the printer resolution, as well as the wall thickness. And there's some minimum gap required between the tubes so that they can actually insert and rotate smoothly between each other. So while the diameters are very dependent on the patient size and the tool size, I want to focus on the curvatures, which are very dependent on the actual material that has been selected. So as I mentioned earlier, if we have two tubes, each with a different initial curvature, and we insert one inside the next, and we end up with this, what we call an equilibrium curvature, where it's somewhere in between the initial two curvatures. And researchers over the years have developed various mechanics models, and so shown here is a relationship to describe the planar case in order to predict what this equilibrium curvature would be given two tubes in this case. And this is based on the size of the tubes as well as their initial curvatures and Young's modulus of the material. And so for our case, what we were interested in is, if we have these tubes, how can we determine what the maximum strain is that this material needs to be able to withstand in order to go from its initial pre-curvature to whatever equilibrium curvature it's going to end up at. And so we derived this equation shown here that's dependent on the material properties of the material that we're actually selecting, and it can allow us to figure out whether a material can actually withstand this amount of strain during the bending. So once we looked at the design requirements, we started investigating a number of different 3D printing materials, as well as actual processes for making these. And some of the main takeaways from this was that we had to better understand the fact that certain 3D printing processes required various support materials to be printed with these tubes. And this became an issue if the support material wasn't dissolvable, because when you're trying to clean out these long, skinny tubes, you risk actually breaking them if the material can actually just dissolve. So we're looking for a process with a dissolvable material or that didn't need any support at all. And then second, we also realized that each process really left various surface finishes on these printed tubes. And we needed one that some of them left in, you can tell here, sort of powdery and rough. And we needed something with a very smooth surface finish that would actually allow us to have smooth insertions and rotations of these tubes with respect to each other. So after printing a number of different samples, we wanted to evaluate whether these materials could actually create tubes that would then behave as we would expect based on the in-plane mechanics model that I showed before. So what we did is we took our robot here and we clamped one of the 3D printed tubes into the distal pin vise. And we clamped an inner tube into this one. And we inserted the inner tube 15 millimeters at a time into the outer tube and then retracted it that same distance. And the whole time we took overhead images in order to then evaluate the curvature and ensure that the equilibrium curvature matched that we predicted. So what we did is we then took these images and we fit two different circular regions to them. So first focusing on this bottom region here, we fit this red circle, and this is the region of the combined curvature. So we would expect that when the two tubes were overlapping, that their curvature would match the models as predicted. And then we also fit this blue circle to this distal region here. And this was just to ensure that these 3D printed tubes could really maintain that initial pre-curved shape that they were printed with, even when you're inserting another tube inside. So here's some results from a few materials at a time. So we have the, for each of these cases, we have a lower curvature and a higher curvature sample being tested. And we could see here that the pre-curved region, shown in blue, maintained this relatively constant curvature throughout the entire insertion process, as we would expect. And the red lines showing the equilibrium curvature matched that pretty close to what we would predict, which is shown, each of the predicted regions is shown in gray here. So the only problem with these materials, that even though they behaved as we were expecting, there wasn't much of a difference between that pre-curvature that it could reach and the equilibrium curvature, because these materials weren't very flexible. So they really couldn't, they didn't have much difference in sort of their bending ability before they would just crack. And so we wanted to investigate more flexible materials, such as these here. But what we noticed here was a trend where we saw with the pre-curved region that there was a slight increase in curvature with an increasing insertion distance, and a slight decrease in that equilibrium curvature with the increasing insertion distance. And we believe that this is probably due to the fact that there's a few reasons. So these materials are much more flexible, and so as we were inserting a stiff tube inside of them, they were unbending quite a bit to become relatively straight. So we're now fitting a very small segment to a very large circle, which could lead to higher inaccuracies. And then we also, these 3D printed tubes were also possible that there was non-constant curvature when we were printing them. And there's a chance that as we were inserting, even though we were commanding a certain distance, it may not have inserted the exact distance that we specified. So we continued looking at more materials because there's more being developed basically every day. And the one that we ended up coming up with is we found this material called polycaprolactone, which is short, PCL is what we call it for short. And this is a highly elastic polyester material, and it's great because it's actually also biodegradable and has been used previously in other forms for sutures as well as for long-term implantable devices. And in addition, we can print this right in our lab, and it's printed without any support material and with a very smooth surface finish. And so the next step, once we found this material, is the next question we wanted to know is, in order to be viable in a clinical setting, could these tubes actually be inserted through various tissues? Because in actual clinical setting, they won't just be moving through free space. So what we did is we had this setup where we have our concentric tube robot here, and we have a tissue, both we did gelatin as well as liver, and it's sandwiched between these two plates, and it's on top of the force torque sensor here. And we inserted the concentric tube robot in this direction through the tissue and measured the various forces. So what we have here are two plots, one for gelatin and one for liver. And so up here it shows the sequence of insertions that we did. So we started with the 3 tubes, inserted all 3 of those simultaneously, then inserted just the innermost tube pair, and then finally just the inner tube. And at each point was measuring the forces. And so what we found is this, as you can see, the red curve in both of the cases shows these curved set of tubes that we did. And those had higher forces, as we would expect, compared to inserting just a straight set of tubes. And then another interesting trend that we noticed is that in both cases for this first region of insertion here, there's a higher increase in force in this first region compared to the other regions. And after additional testing, we realized that this is most likely due to the fact that in this first insertion phase, we're inserting all 3 tubes together, and this outermost tube has a larger diameter. So this larger diameter tube causes higher forces on the tissue compared to the smaller diameter tubes. And we also noticed that sometimes when you're inserting the larger tubes, there's a slight fracture of the tissue at the proximal tip of that larger tube. So then when you insert the next set of tubes after that, there's a slight decrease in force because the tissue is slightly fractured at that region. So the main takeaways from these experiments that we found was really that, yes, our 3D printed tubes could withstand these forces that we needed to drive through these tissues, and could drive through even inhomogeneous tissues such as liver in this case. So now that we've designed and fabricated our patient-specific tools, the next step is how do we actually control them in a procedure? So in order to drive these concentric tube robots, we need to be able to control both the insertion and the rotation of each of the tubes individually. So many groups have their actuation systems use a lead screw and a linear slide type mechanism to control the translation degree of freedom. But you can imagine if you're trying to control 2 or 3 or 4 of these tubes at once, your design can get rather large and bulky as you're adding these together. So we were interested in developing a smaller, more compact mechanism for driving these that would also be more conducive to a patient-specific design process that we were interested in. So what we developed here is this more modular actuation system. So you can see at the bottom, this is 3 modules, and each one can hold a single concentric tube robot, and then can be attached together in order to create the entire robot for driving these concentric tubes. So zooming in closer on just one of the modules, some of the main features are at the this end here. This is where we mount one of the concentric tubes. And then we can see here that at the bottom, there's these module attachment bars. And then a feature that we can't see are these male-female alignment features for aligning each of these modules together. And then you can use these bars to attach them. And then in the middle here, we have this roller gear. And so this is basically, you can see there's this kind of waffle or grid-like pattern on it. And then we have 2 spur gears oriented orthogonally to each other here. So the way that this works is if we rotate the top gear here, we can get the insertion as well as the retraction degree of freedom. And then if we rotate the bottom spur gear, that's how we get the rotation. So with just this single module, we can control 2 degrees of freedom for each of the tubes. And then one of the nice features about this as well is that each of these modules can actually nest one inside the next as well, just like the concentric tubes. So that's how we get this much more compact design. The next step is we wanted to make sure that we wanted to measure what the accuracy was if we were driving these under various loading conditions. So we used an electromagnetic tracker and sensor to sense the position, and then we used here the same force torque sensor. And so for on the left here on the position case, we inserted we commanded an insertion of 15 millimeters at a time against various loads, which we applied with an airline and a syringe, and there was less than half a millimeter error for all of the insertion cases against the various loads. And similarly for the rotational case, we commanded various rotations, different angles against a torsional spring, and there was less than 1.5 millimeters, or 1.5 degrees error for the angular case. And so the next step is we wanted to make sure, could we actually drive a set of these concentric tube robots to various target locations? So we chose 3 target locations and drove the concentric tube robot to it 3 times for each of the cases. And what we found is that we could drive it to the target with about less than 2 millimeters error on average each time, which is reasonable for our particular application where kidney stones are on average about 12.5 millimeters. And we believe that we can reduce this error even further by having a human actually teleoperating this to the target, and also by actually implementing closed loop control on the tip of the robot. So in this cases, we were only using control based on the actuators and the encoder readings, but if we used imaging or some other sensing on the tip of the robot, then we could improve this further. So then looking a little bit into what this enables in the future, is we've been thinking about a way that we can actually miniaturize our system even further. So if we actually integrated this sort of gearing teeth pattern onto the straight length of the tubes themselves, then we could, and use that for the transmission, then we could actually make a system that is barely larger than the tubes themselves in order to actuate it. And when we think about sort of even with our current system, which is much smaller, what that sort of enables in terms of new interactions and interfaces for the surgeon, we thought about whether you could maybe even just attach it to the arm of the Da Vinci in order to increase the number of degrees of freedom that you can use there. Or what if we had someone actually having a handheld version of this, what would that look like? And what are these new sort of interfaces and interactions that we enable by having this smaller, more compact version? Okay, so now that I've walked through the different steps of our patient-specific design process, I want to go through a demonstration that we did in a phantom patient model to show this process from start to finish. So again, the task that we were interested in this case was accessing this renal tumor. And our goal was to design this patient-specific concentric tube robot to get to the tumor. And then we would stick an ablation probe through this concentric tube robot, and then left for future work would be actually ablating the tumor and getting rid of it. So we had our pediatric urologist. So first we set up this actual patient model. So again, we used the same CT scans from this 9-year-old boy that we built up the digital model before, and we actually made a physical model mainly out of 3D printed parts. And so shown here are some of the important features, like this last rib that we're actually trying to avoid and curve underneath. And you can see the liver shown here, as well as we put up skin layers, so it's basically plastic skin to represent this back layer. And then we made a gelatin kidney, so we made it out of gelatin so we could actually drive through it rather than having it be a hard region. And embedded inside the kidney are some of the internal structures that were also 3D printed. And zooming in a little closer, because it's hard to see, we embedded a gelatin tumor as well inside the kidney, and that was the target that the surgeon was actually trying to reach. So we first had him use the design interface to design 2 different sets of tubes. So the first one, highlighted in yellow here, is basically this C shape, and it was curving under, shown in blue here, this 12th rib. And then the second set he designed was more of an S-shaped curve, also highlighted in yellow here. And it was also trying to curve under the rib and into the kidney. And this is that same design, just shown from a side angle, so you could really see the accentuated sort of S-curve that he created. And looking a little bit closer and wanted to see what some of his interactions were like when he was actually in this design process. And so you can see that during the initialization stage of the process, so shown in gray here, he spent a lot of time actually switching between placing those via points and changing the camera angle, actually. So he would place a point, look at it from a different angle, and try to make sure sort of what he was doing the entire time and see what it was like with respect to the anatomy. And then once the design was initialized, he then spent the majority of the time after that changing the parameters of the tubes, as well as making sure, moving the concentric tube robot around to make sure that the sort of insertion point was correct with respect to the anatomy. So then once he finished the design, we actually 3D printed these tubes in our lab. So here's the midway through the printing process. You can see this is the extruder here and a close-up view of what the parts look like as they're midway through the print. And the nice thing is once they're done printing, we basically just take them off the tape and they're ready to use. And we attach them directly to our actuation module shown here. And we put our whole actuation module on this arm actually, so it makes it a lot easier to maneuver and orient it with respect to the patient anatomy. The next step was to actually have the surgeon teleoperate these concentric tube robots to reach the target. So the way that we set this up is we had him use the phantom omni, and we used the position and orientation of the omni to actually control the movement of our concentric tube robot. And we could use the encoder positions to send back. And so as the surgeon rotated this last link of the omni, that corresponded to rotation of all 3 of these tubes together. And then as he inserted the last link of the omni, that was the insertion of these 3 tubes. And we wanted to try and give him a way of most closely approximating this follow the leader type insertion that I was talking about, where the backbone follows the tip. And so to do this, we used the buttons on the omni. So we enabled him to, if he was pressing down both buttons together, that would enable him to easily insert all 3 of these tubes at the same time. And then similarly, if he was just holding down one, he would just do these 2. And then similarly, he could just control the insertion of the final tube itself. And the nice thing about this as well is that there would be no movement of the robot unless he was pressing the buttons. So it's sort of a self-touching type system. And so what we did is, I want to show an example of one of the deployments of one of the sets of tubes that he designed and that he printed. So focusing on the kidney here, you can see highlighted in blue what the concentric tube robot looked like when it punctured through this sort of skin layer and into the kidney. And again, a front view of it and one from the side. So avoiding this rib, entering into the kidney and into the tumor region. And we have a close-up of what the tumor looked like as well when we accessed it. And we actually then, once we realized we hit it, he stuck an ablation probe through the center of the concentric tube robot and into the kidney itself. And so then the next step would be to actually ablate this tumor in order to demonstrate actually getting rid of it as well. Okay, and so with that, I want to conclude with a short summary of my work as well as the contributions that I've made. So starting with some contributions of the development and demonstration of this patient-specific design paradigm, which was really aimed to address unmet needs of specialized patient groups. Second was the development of this design interface that is aimed to actually leverage the surgeon's expertise in the design process. Third was the validation and use of additive manufacturing or 3D printing in developing these personalized concentric tube robots. And finally, the development of this modular actuation and control system for driving these flexible medical robots as well. So thinking back a little bit to the current generalized robotic systems that I was talking about at the beginning, what my work, I believe, has really enabled is this new patient-specific design paradigm, which I believe we can view as a complement to the existing systems. And whereas this may not have been feasible to do in the past, I think new technologies, including new fabrication methods and virtual reality, et cetera, have all sort of enabled us to have this potential of a future filled with more personalized robot design. And I believe that this paradigm can extend beyond just surgery to a range of other applications as well. And that with these new personalized, customized robots, we can start to think of other questions in terms of what are the most intuitive ways of interacting with these robots and what the control interfaces actually look like. And finally, I think that it enables us to think about new robot designs and how can we use these new technologies to actually make new, more customized and patient-specific robots. And so with that, I would like to make some acknowledgements. I'd like to thank all my committee members and meeting committee members, as well as our collaborator, Dr. Mike Shea, who couldn't be here today since he's on the East Coast, but he's helped me a lot with all of our work. I want to thank my funding sources, and then, of course, my advisor, Allison. Thank you so much for all your support, research, and running, and everything. I couldn't have asked for a better advisor. I feel very lucky. And then, I don't know. I would like to thank my old, incomplete without a tribute to my old office mates, Nick, Troy, and Kirk, without which I would not have learned what life as a PhD student was really like. I am now able to work in any environment, no matter what the distractions are. Yeah, so thank you. I have to thank my running crew, of course. I don't know, I'm pretty sure you guys have listened to me babble about nonsense for literally thousands of miles, waking up before the sun gets up, so thank you guys for everything. I want to thank my housemates too. Andrew, if you're watching, we miss you. Yeah, and Evan as well. And of course, I have to thank my best friend Jessica for everything. Since middle school, you've been one of my biggest cheerleaders. And yeah, life would be way less fun without you. I'd like to thank my family as well, everyone who's here. And yeah, it's been great coming back to Stanford since I grew up in Mountain View, and living close to home has been so nice now. Get to see everybody a lot more. So thank you guys for putting up with me and supporting me through everything. And finally to Grant, I know I can be a lot to put up with, and I can be tiresome at times. And you put up with my bad ideas, like 40 miles of hiking, and you're always the one standing there by my side. So thank you. And with that, I'll take any questions.
So I think a quick answer, anybody who hasn't been in these events before, just quickly, we have a short Q&A session. It's open to everyone, and then we'll ask you to go. And then we'll pass it over to something to you to share.
Thank you. Over there. Yeah.
In your presentation, you mentioned it takes about 6 minutes for the first time your surgeon went around and did the design, and then 200 seconds for the second time. But how many seconds did it actually take to teach him to use the device and all the haptics involved?
Yeah, that's a good question. Surprisingly, a lot faster than I would have thought. I think being a surgeon, he's very coordinated and used to these types of sort of a lot of movements at once. And it actually took him I think we maybe spent half an hour or so getting him used to things. And then each time he would come back, I might have new interactions for him to learn, and those would take another 15 minutes or so, but it was relatively quick.
So building off that, with the practicality of doing this large scale, would you have one surgeon design the robots for every patient, or would each surgeon for each patient be the one designing it?
That's a good question. Yeah, I think in general, people, I would assume that maybe they would want the same surgeon sort of designing it and taking it through the whole process, since they're really designing it for also how they would best approach the problem and what approach they might take to actually reach the site. So I would envision it as the same surgeon doing it for one patient. So that's a good question. We've also thought about whether for certain patient groups you could actually create sort of a whole set of these like concentric tubes, for example, and that the surgeon, rather than designing the individual tube parameters, could select from that set the right ones for the patient.
How does the surgeon know where to start the robot? Like, how does he locate the via point on the patient?
You mean in the design interface or in the physical world?
Moving to the physical world, like you pick the via point in simulation.
Yeah. So basically we try to register the robot, so like I'll set it up, registering it with respect to the patient anatomy the same way that he had it set up in his interface.
So the other groups work on optimization problems for designing these. Have you compared what kinds of things are different when you have the design expertise of the surgeon to what you would get if you just did
No, we haven't. That's a good question. I do think that there's also room for combining the two together possibly. So maybe starting with an optimization algorithm as the initial design and then letting the surgeon maybe tweak it based on what they think makes the most sense for the procedure. But no, that's a good question.
Given that there's a design phase with the surgeon planning what happens, would there be any benefit to automating the control of room surgery?
Yeah, so actually we did look at that as well, but so the interesting thing about that is that if everything isn't exactly the same as it was when you designed it, then you actually do want the human in the loop to actually account for some of those errors and teleoperating it in order to reach the target. Yeah, so.
You've shown 3 also in most examples.
Mm-hmm.
Is 3 done as an optimum? Have you tried more?
Yeah, so I think I think the most I've seen used in the literature is about 4. I think with that you can access basically everything that you need. I think there's quite a few cases of people using 2, and often they'll use just a straight outer one and then a curved inner one. But 3 sort of seems to be kind of at least a good example that's in between.
One more question. Yeah.
In terms of the fabrication, did you look at how the resolution of the 3D printer reflects?
Yeah. So there's definitely a small difference between the design parameters and then what you actually print. And so we did looking at some sort of error propagation between what that error is and how that would affect then, say, the tip position of the robot. But it is relatively small, and if you get better technology as well, then those errors will become even smaller. And you can also account for it in the design process if you know what those are going to be.
You have a lot of questions.
Is there any way that you, I guess in the initial design phase, you have the stiffnesses of the tubes?
Mm-hmm.
Is there any way you could do like a density kind of scan to also sort of know what the stiffness of the surrounding tissue is and how that could guide you?
Yeah. So I think the whole sort of tissue elastography and figuring out tissue mechanical properties is another huge research area that's too much for us to add in. But I do think that is the next step, is to add in what are the effects of the surrounding tissue, and how does that affect the actual design of the tubes? Yeah, no, I think that's definitely a good point.
All right. So we're going to take a 5 minutes break, and then we resume the closed session. Thank you. Thank you.